These are the two postulates of special relativity. You can think of the first one as your ability on a train or an airplane, a moving train or airplane, to pour yourself a drink just as easily as you could pour yourself a drink when you were quote-unquote stationary in a diner. So the way this is stated usually is that the laws of physics for all inertial reference frames are the same. Inertial here means not subject to any sort of acceleration, and that acceleration would include gravity. So if you're accelerating in a plane, it'll be different than if you're on Earth non-accelerating. And that's not really a principle in and of itself. It's more like a counter principle because we're used to walking around on the ground and referencing everything with respect to the Earth, which is relatively stable. And so it's kind of negating that notion that the Earth is some kind of privileged reference frame. In reality, if you're in a plane, it's just as valid for scientific experiments as any other experiment here, on the ground. All right, so we're going to talk about that with what's called the Galilean transform, because Galileo understood this principle and he wrote about it. He was talking about the motion of butterflies on a ship, how they can float about and flutter just as easily as if they were fluttering about on land, even though the ship is moving. So here we have the K-primed frame, which Alice is in, and we're going to superimpose Bob on Alice. So Bob and Alice are hanging out together, and Bob will be in the K-primed. So at time equals 0, Bob starts moving away from Alice in the positive x direction. Just like that. So he's moving with a velocity v in this direction. This is Bob. He's moving with a velocity v, so he's moving away from Alice. He sees Alice moving away to the left. Alice sees Bob moving away to the right. And the way the Galilean transform is written, if you want to find an event in Bob's reference frame, you can take measurements from Alice's reference frame, the unprimed frame, and convert it to Bob's reference frame. So we'll say the event happens at 1 meter according to Alice. See, 1 meter away to the right. And Bob looks like he's maybe 8 meters away at this point, so we can say he's been moving 2 meters per second. He's been doing that for 4 seconds, so now he's 8 meters away. To get the event from Bob's reference frame, we take the measurement from Alice, this x, which is about this far, x minus velocity times time, which is this far. So Bob never measured how far it is from him. He asked Alice. He got Alice's measurement. He knew how fast he was going. He knew how long he's been going. So now from that he can derive, or maybe derive is not the right word, conclude how far he is from Alice, from the event, not from Alice. Also from Alice. So that would be 1 minus 8. It is -7 from Bob. That would be the coordinate for Bob. The same thing for Alice. If Alice wanted to know where an event happened, and Bob could tell her, and she knew how long they've been drifting apart and how fast they've been drifting apart, Alice can find out where the event would be with respect to her just from the information from Bob, knowing the velocity, knowing the time. It seems like a lot of work, but we're building the basis for special relativity here. And so that's how you can translate events from one reference frame to another reference frame in just traditional Galilean transforms. Now what we want to note here is that an event can also be, let's say, a light pulse. We can express distance as a function of velocity times time. We kind of did this here. These are all units of meters or feet. So what if the event we're talking about is the position of a photon? C, the speed of light, and t is the time that we're measuring from. So we go from the unprimed frame to the primed frame. And here we go from the primed frame to the unprimed frame. Here we're talking about a photon, so CT equals CT prime plus vt. Now, in a Newtonian world, this would work perfectly. Bob would measure the photon over here, and Alice would measure the photon over here. The problem comes about is this second postulate here. The speed of light in a vacuum is constant. Because they were together at time equals 0 and they started drifting apart, it doesn't matter how fast Bob is moving to the right, or from his perspective, Alice to the left. If Alice sees a photon moving if Alice sees the photon 1 meter away from her, Bob will see the photon 1 meter away from him, because the speed of the photon doesn't change with respect to anybody's motion. That's the one thing we have to hold constant. And we're about to see that if we hold the speed of light constant, we have to make other things, space and time, variables in order to reconcile that pseudo paradox. So we cannot prime C because it's the same in both reference frames. So we're going to get rid of that, but we're going to keep the prime on the time variables. We're going to keep this prime because remember we said that space and time will depend on the observer. So we're going to have to distinguish between primed and unprimed time now, which, as you can see, we didn't do that here in this transform. So CT prime equals, I know what I'm about to do, so I'm going to write this over here, CT minus VT. And same thing over here. Just like that. So this won't work because still Bob is going to see the photon over here and Alice is going to see the photon over here. They both need to see the exact same coordinate for the photon. So we're going to introduce a simple linear transform to both of these here. And quick thing, gamma is going to be the same for both of them because the situation is symmetric. Bob sees Alice moving away at the same speed. Alice sees Bob moving away. By the same token, V is going to be constant for both of them because if I see something that's 10 meters away from me, that same thing will see something, will say that I am 10 meters away from it. It's a completely symmetric situation. It's the same thing for velocity. So what we're going to do is solve for gamma and see if this can solve our problem and what we get from that. So we're going to divide both sides by c in both of the equations. Then we're going to factor out a t here, and we're going to factor out a t prime here, and then we're going to combine them. So here we have t prime equals gamma times t. We factor out that t. 1 minus, we factored out the t, so it's just velocity. Remember, divide by c. We divide by c here and here. And the other equation, same thing, pretty much. T prime times 1 plus v over c. Not squared. Not yet. We'll go ahead and we have a t here. We're going to replace that t with this t, or this whole bit. So we have t prime equals gamma squared, we included that, times, and we're substituting in the t right now, times t prime, included that, times this whole bit, 1 plus v over c, and now we include this bit. 1 minus v over c. And this is very, very pretty mathematics because you'll notice we have a t prime on both sides. That cancels out. And we have a nice conjugate here. So that'll be good multiplying. So 1 equals gamma squared. The conjugate multiplied out looks like that. And we can solve for gamma. And I'm going to do this all in one step, just because 1 minus v squared over c squared. So that's our gamma factor. So we can take that, and using this equation here, we can solve for the event. And actually, so that's equivalent, the gamma is also in this equation. So we want to solve for the x coordinate according to Bob. if he has the measurements from Alice. It'll look like this. X prime equals gamma times x, this is the knowledge he gets from Alice, v times t. Or x minus vt 1 minus v squared over c squared. So multiply by the gamma factor. And this is a very special case here where they start at t equals 0 and then you're coordinating reference frames, but you can use this to go ahead and build more complicated systems. Actually, I'm going to keep this here. Just make some more room here. So here we were only talking about the x-coordinate, just the coordinate in one dimension. And if we do that, the y and z coordinates, they are the same. Now the time coordinate, we use ct prime equals ct minus vt. So we kind of do the same thing here. So we're converting time now, finding the time transform. Ct prime, divide both sides by c. T, and forgot the gamma here, but the gamma is included on each of these transforms to make it make sense. Minus vt, remember we divided by c. And here you can replace, remember velocity times time equals distance, x. You can replace time equals x over v. So what we're talking about here is the speed of light. This t. So this one's maybe a little bit more confusing. C times t equals x, because we're talking about the photons. So t equals x over c. So the way this is commonly written, I'm just going to expand the gamma factor. 1 minus v squared over c squared in the denominator here. T minus, okay, v times, okay, t, replace the x up here, and there's the c, and that's going to go straight to the numerator here. And so that's the way the time transform is written. This part is still a little bit weird for me, because I'm not sure if that's when the event did happen or when Bob sees the event happen, the distinction between that, or if they're actually the same thing and I'm just not getting the philosophical implication. But anyway, that's the transform that you're probably going to need on your test. And so that's how to derive the gamma function. And we'll probably do another video on a different way to derive it, maybe kind of easier way to think about it with a thought experiment involving a light clock in the next video. But that's how you can do it. And I hope you enjoyed. Thanks for watching.